Good afternoon and welcome to MOS Live. My name is Katie, my pronouns are she, hers, and I'm going to be keeping an eye out for all of your questions about Earth science today. If you're watching on Facebook or YouTube, thank you so much for joining us, but please know that we can only see questions from Zoom at this time. If you're watching on Zoom, you can head to Q&A at the bottom of the screen to type in your questions to our scientists. And if you'd like to include your name and age, we can give you a shout out if we get to your question. If you'd like to see closed captions, please head to the bottom of the screen and click closed captions or CC to see those. At this point, I'll invite my presenters to turn on their cameras and introduce themselves.
Hi, everyone. My name is Becca. My pronouns are she and her. And my favorite part of Earth science is everything having to do with geology. So I really like rocks and minerals, plate tectonics, and I love volcanoes, as you can probably see from the background behind me. So feel free to put in any questions about that.
Hi, my name's Eric. My pronouns are he, him, and my favorite part of Earth science is comparing the Earth to other planets in our solar system. We know of oceans and volcanoes and weather on other planets that is somewhat like the Earth sometimes and completely different other times. And I think it's fascinating to compare.
Hi everyone, my name is Sarah. My pronouns are she and her. And when it comes to earth science, I really love the oceans and talking about the water on our planet and oceanography and ocean biology and all of that fun stuff.
Thank you. Eric, you mentioned some different planets out there. Are there planets that are similar to Earth that we can compare?
So there are. Venus is the closest planet to Earth in size. It has an atmosphere, air like we do, but it's much thicker. It's 100 times thicker, and it acts like a blanket, heating up Venus, making it the hottest planet. And it's made of completely different material. Mars is a lot like the Earth too, but the atmosphere is a lot thinner. Mars is a lot smaller, and we think both Venus and Mars at one point had active volcanoes. There's also a lot of other places in the solar system that aren't planets, but moons of planets, especially the really big planets like Jupiter and Saturn. They have worlds going around them, many moons, dozens of them. And the moon Io of Jupiter has hundreds of volcanoes. It's the most active place we know of in the solar system. Europa is another moon of Jupiter that has an icy crust and liquid water underneath. So if you go different places in the solar system, you can get some pretty strange places that look a little bit like Earth.
Thanks. And what does the very inside of the Earth look like?
That's a great question. And it's something that scientists always want to know. So inside Earth, we have a few different layers. We have an inner core, we have an outer core, and we also have a mantle, and finally the crust, which is what we are sitting on right now. We're sitting on the crust of the Earth. Now, the crust is a little bit different depending on where you are. There's the oceanic crust, which is much thinner. It's only about maybe 7 kilometers thick, whereas then you get the continental crust, which can be up to 40 kilometers thick. So a lot of different things happen as pieces of crust kind of are moved by parts of the mantle underneath. But there are a lot of different layers, and the Earth is very dynamic and constantly moving because a lot of those parts of the inside of the Earth also are kind of moving.
From Jacob, who is 5 years old, what is all the black stuff in lava?
That's also an excellent question. So the black stuff is also technically lava, but it has cooled. So when lava or any rock is molten, we call that lava. So lava is just basically molten rock. But as it starts to cool, then it turns black because it becomes a rock. So when you see lava flows that might be moving really slowly, you might see that the outer part of the lava flow is dark and that pieces of it may break off with the rest of the lava flow, but that's just cooled lava. So that part is already solid. It's no longer a liquid. And so it's basically all the same thing. It's just different minerals within that rock that have cooled, but it does look kind of cool. It looks like there's 2 components, but really they're just the same.
Thanks. And I might have one more related question for Becca. How are mountains formed?
Oh, that's a great question. And mountains can be different from a volcano because when mountains form, most of the time they're two continental plates. So I was talking about how there's different types of crust. Well, the crust is also broken up into things called plates. And when two continental plates kind of push against each other, they're both they're both really thick. So neither one of them can really go underneath the other one all that easily. So they kind of end up pushing up and kind of like that. And they just get taller and taller. Now that's what happened when the India continental plate pushed up against the rest of the Asian continental plate. And that's what created the Himalayas. And that they're pretty recently new. So that's why they're so incredibly tall, because that process had happened, well, recent on a geological timescale, but it's a little bit different than volcanoes, where oftentimes oceanic crust would go underneath continental crust, and you might have some volcanoes pop up there, or in a divergent boundary where two plates kind of move apart from each other, could pop up there, or even just from a straight mantle plume, which is basically like one little area, one little bit of magma coming up from the mantle to form a volcano. So volcanoes happen in a number of ways. Mountains are a little bit more tricky, and they tend to happen mostly from two continents pushing against each other.
And are there also mountains in the oceans?
Yeah, so Becca just touched on it a little bit. Our mountains in the oceans are usually because of a divergent plate. So the two plates coming away from each other, causing the magma to come up. So we usually sometimes like to call them underwater volcanoes. And the one that you may know best or have heard of before is the Mid-Atlantic Ridge. So that is the one that goes right down the middle of the Atlantic Ocean. It is really tall, and it actually has a lot of life there, believe it or not, because there is a lot of heat coming out and a lot of minerals coming out of the earth to have life so deep in the ocean. So there's these huge ridges under the water that are caused from volcanoes essentially coming up and solidifying and forming to create this huge mountain in the water.
And where do craters come from? How are those formed?
So craters are something that is caused by an impact. Most craters that we see on, say, the surface of the moon happened when an object that was flying through space hit the moon and went from having a whole lot of energy of movement to not moving at all. All that energy has to go somewhere, and so it goes into heat and light and basically a big explosion on the surface. And we can get craters formed from things smashing into a surface that are much, much smaller than the crater. We do get craters here on the Earth. They're not as common because they get erased by Earth's oceans and the wind and all kinds of different processes that we have, volcanoes resurfacing the Earth. Over the course of a few thousand years, a crater can pretty much disappear. On the moon, craters are billions of years old and pretty obvious because there's nothing to erase them. But on the Earth, we have one really great crater called Meteor Crater in Arizona. It's huge. You could fit several football fields inside of it. And we think it was formed from the impact of something the size of the Museum of Science. So one building sized object that was really dense and made out of metal coming in with enough energy to blow a giant, nearly mile-wide crater into the ground. So we're taking a lot of energy, getting rid of a lot of the material on the ground, just simply throwing it up or vaporizing it, leaving behind a great big hole.
Thanks. And again, looking maybe out from Earth, what is a solar eclipse?
So that is when we have the moon moving between us and the sun. And it's an eclipse because all three are lined up perfectly. So the moon happens to be around the same apparent size in the sky as the sun. The sun is a lot bigger than the moon, but it's a lot further away. And so they look to be about the same size. When the moon goes around the Earth, most of the time when it lines up with the sun, it's a little bit above or below. And so it doesn't block out the sun every single time. But every year and a half, the moon goes right across the path of the sun, and the three line up perfectly. The moon casts a shadow on the Earth. That shadow is total, meaning the sun is completely blocked out for a really small part of the Earth, not the entire Earth, but for one small part, a path that shadow travels through, maybe 30 miles wide, if you happen to be in that path and look up at the sun, the moon is completely blocking it for maybe 3 or 4 or 8 minutes. So we had the first really good one here in the United States a couple of years ago. It went all the way across from the Pacific Northwest all the way down south. We've got another one coming up in a few years. It'll be a little bit closer to home. The path goes right through upstate New York, New Hampshire, Vermont, Maine. So we'll be able to see it from places in New England. And it's supposed to be one of the most spectacular sights ever. So hopefully we get that. I think it's coming up in 2024. Hopefully we get good weather and we'll see a great display.
Thank you. How are lava tubes made?
That's a great question. They're really interesting too. And Eric might be able to talk more about lava tubes elsewhere potentially. But lava tubes on Earth are fascinating because what happens is when lava is moving, as I said earlier, that black stuff on the outside is when it starts to cool. So pretend that this is like lava going through a tube, and this outside part is starting to cool, and it kind of leaves behind a shell of the outside of the lava. So really what the tube is it's just cooled lava, but the inside is still molten. And so it starts to flow and continues to flow all the way, making this really long tube. And lava tubes can be anywhere from very small to very large. In fact, I've been inside one that is really, really large. It's at least probably 10, 12 feet tall and wide. So they can be even larger than that, but they're definitely very interesting features.
And we've found evidence of them on places like the moon and Mars, which is great because if we want to go there and live for a long time, we need to keep the astronauts safe from all kinds of things. And one of them is radiation from space. If you go underneath the ground into a lava tube, there's a previously existing big open space that has dirt above it, which is a great way to stop radiation. So we might use lava tubes that we discover on other worlds in the solar system as a place to set up a base camp and explore that place.
Thanks. All right, I have 3 more lava questions. So we have from Prisha, who is 8, why is lava so hot? And then we also have, how hot is lava? And how close can a human get to the core?
Ooh, those are all good questions. So lava can be over 2000 degrees Fahrenheit. That's pretty standard that it's going to be just over that, maybe a little bit more, depending on where it is. And so lava gets really hot because there's a heat source in the volcano. In fact, that heat source is coming directly from the mantle underneath the crust, and it's incredibly hot down there. Just not as hot probably as the core would be, and we can't really get too far. In fact, no humans have even been into the mantle. So the closest we could get to that would probably be if we could get down to that mid-Atlantic ridge or somewhere that is very close to a spreading center, a divergent boundary in the ocean. That would kind of be the furthest down to the mantle as possible. And I don't think any people themselves have been there, but definitely they've sent other robots and things that could go and see that. But lava's hot because there's that heat source making it molten rock. And if rock's going to melt, it has to be hot. So it's just hot because of the way that the volcanoes form. But definitely really interesting and definitely varies dependent on where it is in the composition of the lava.
Where do diamonds come from?
That's a great question too. Diamonds are made of carbon, much like graphite is. But in the case of diamonds, the carbon has to be under very, very extreme pressure. So it has to be kind of in a situation where there's maybe other rocks or other things sort of pushing on it in order to get it to form the exact mineral structure that it needs to create a diamond. Because if it forms any other mineral structure, as carbon really does, because there's so many different types of carbon out there, it would potentially form something else. So something like graphite is easier for it to form. And so it takes a lot more pressure to get it to actually conform into the perfect diamond structure. And so that's why it's pretty rare. It just needs to be in a situation that is absolutely perfect in order to form.
And moving a bit further up, how do glaciers form?
Yeah, so glaciers are ice. So they form when it's really, really, really cold. Glaciers are usually, wait, correct me if I'm wrong. Glaciers are usually on land. Icebergs are in water. Is that correct?
Yes.
So I think that's it. It's something like that. So glaciers form when it's really cold, and icebergs also form when it's really cold. Icebergs, I believe, are a little harder to form because salt water needs to be colder to get ice because of the salt that's in the ocean. So there's a lot of salt, there's a lot of minerals in our ocean, so it doesn't freeze as much. It also moves a lot more. So that's why things like lakes and ponds are going to freeze over before an ocean ever does. And we usually only see these things in our poles. So at the top in the North Pole and in the South Pole as well. Glaciers are usually, I believe, I would need to look this up again, but they're usually from some sort of freshwater source on the land that ends up freezing over a long period of time. And glaciers can also move across the land, and that's how we have a lot of our landforms that we see today. And so glaciers form by essentially freezing water. And then they melt when we have a lot of warming, either from the summer being warm or also from our Earth getting warm as well.
I think this is kind of a big question, Sarah. How does the ocean affect us?
That is a big question. The ocean, I guess, affects us, or affects, I'll say it as the Earth first, and then maybe us as humans. The ocean affects the Earth in a lot of ways. It essentially drives a lot of, or most of, our weather. So weather is usually coming from the heating and cooling of water and the movement of water vapor and the movement of our winds. And so our oceans drive a lot of that system. So our oceans are hotter around the equator, which means that there's more evaporation of that water. It cools as it rises, and then it's going to fall in a different part of our Earth. So although the equator is where the evaporation is, that's not necessarily where it's going to rain. And so that happens along our entire Earth. So our oceans are driving our weather, our extreme weather patterns, and also our daily weather, also our climate over time. How the oceans affect us, we actually get a lot of our resources from the oceans. So we not only get food, a lot of people, I don't remember the statistic right now, but it's something like 1 in 8 people rely on the ocean for their main source of food. So that's obviously a huge thing the ocean gives us. But the ocean actually provides us a lot of oxygen as well. We think over 50% of our oxygen that we breathe in comes from the ocean. So there are these small little microscopic plants called phytoplankton that take in carbon dioxide and release oxygen. And there are billions and billions of phytoplankton across the entire world that are providing us our oxygen. Oceans also bring us a lot of cool things, like a lot of new medicines and a lot of cool compounds that maybe we didn't know about before. A lot of those come from coral reefs or other areas. So the ocean does a lot for us. We also, especially in America, I think it's most of us live by the coast. Our most densely populated areas are along the coast. So not only is it providing us a lot of stuff, but we also just love to be there. There's a lot of tourism. There's a lot of places that we just love to live. The ocean's a great place to be.
Thank you. Jumping back to diamonds, actually, Aditi, who is 10, wants to know, can Jupiter form diamonds?
Yeah, so we haven't discovered any. We don't have a picture of a diamond inside of a gas giant atmosphere. But when we do the math to figure out what the conditions are in a gas giant deep within it, it turns out that it's very similar to conditions underneath the Earth. If you just need carbon and you just need a lot of pressure, well, deep inside of a gas giant planet, those two things exist. And so there might be places in the universe on exoplanets, which are planets that are going around other stars, where not only do diamonds form deep within them, but they actually kind of form out and then rain down. So you might have an exoplanet where diamonds rain the same way that water rains here on the Earth. As far as Jupiter, you probably have to go pretty deep to find them, because even though it's a big, impressive planet, we found other much bigger ones going around other stars. And if you wanted to go get a Jupiter diamond to have a really unique piece of jewelry, you'd probably be out of luck. We don't have anywhere near the technology to be able to go that deep into Jupiter where the conditions are that extreme and bring one back up. Looks like you're still muted, Katie, if you're trying to give us our next question.
Or perhaps Katie has disappeared.
Well, I know, Becca, you like to talk about one volcano in particular, which is the Yellowstone volcano. And I know that we were talking about it before. So why don't you tell us about what makes that such a unique volcano?
Sure. So Yellowstone is definitely my favorite volcano, and it's for a number of reasons. A lot of people don't even realize Yellowstone is a volcano because it's America's first national park, and it's really cool, but it is. It's a super volcano, which is a really big term. It basically means that it is a massive volcano, and it's formed kind of like the Hawaiian Islands, where there's kind of this mantle plume, this plume of magma coming up from the mantle. Except instead of the Hawaiian Islands being a plume coming through about 7 kilometers of ocean crust, this hotspot's underneath the continent and has to go through up to potentially 40 kilometers of crust, which means as it makes its way through, it's going to build up a lot of pressure and continue building and building and building and building until eventually a massive, massive eruption. Now, that is something that is probably not going to happen anytime too soon because it is an incredibly well-monitored volcano. It's a national park, so we have perfect access to figuring out exactly what's happening there, and a lot of scientists monitor it regularly. Although it does see some really interesting activity, including some increased activity with Steamboat Geyser in the past few years, just due to some different changes in where the heating from the magma source are. But it's definitely a super cool volcano, and I love talking about it all the time.
Oh, hey, everybody, this is your host, previously unseen. My name is Talia. I use she, her pronouns, and I've just heard from Katie that her internet is out. So if nobody minds, I can take over for her asking these questions. And we have a question here for Sarah. The Brown family would like to know, why does the ocean have salt in it?
Yeah, that's a great question. So salt is sodium chloride, which are minerals, and a lot of those minerals are found in rocks. So the reason that our ocean is salty is because over time, rocks have been weathering from either rain or running water or a lot of other things, sun even, and that has been slowly coming from our rivers into the ocean. So over time, our rivers have been dumping more and more minerals, or in this case, sodium and chloride, into our oceans over thousands and millions of years. And there's so many rivers that it keeps running out into our oceans. So our oceans have become salty. Our oceans are around 35 parts per thousand, which means that if you had 1,000 buckets, 35 of those buckets would be salt. But different areas are actually saltier than others. So usually parts of the ocean that are hotter have more evaporation and it leaves that salt behind and makes it saltier. Even areas of the Arctic, I was talking about the icebergs before. When it's cold enough, the water or the H2O freezes, but that leaves the salt behind. And so it's a little saltier in those areas as well. But when we see melting, then our salt tends to change. So it's saltier and not saltier in different areas of our ocean, but on average, it's about 35 parts per thousand.
Excellent. And we've got actually a couple of, I guess it's an interesting sort of thought process. If instead of a molten core, we had, say it was solid, like rock or metal or whatever the core is made up of, if it wasn't molten, if there was no lava, would there be life on Earth?
That's a great hypothetical question. And we could probably all even add to that. My initial guess would probably be no, because in order for there to be life, I mean, we have we have to have water, we have to have air in our atmosphere. We have to be the right distance from the sun, although that probably wouldn't change. But we need that based on how our Earth works. We probably wouldn't have had volcanoes at the very early Earth providing enough water in our atmosphere to create oceans. So it's possible that Earth would be completely different, although I know there are probably other planets out there that are similar to that scenario.
Yeah, we think Mars used to be a lot more like the Earth and have a kind of liquid core that produced a magnetic field and protected its atmosphere from the sun's blasting radiation. And then that cooled down more quickly than the Earth because it's smaller and solidified. And so we didn't have a magnetic field on Mars anymore. And so the atmosphere was lost. Mars used to have a much thicker atmosphere. We think it used to have maybe a lot of water on the surface. That water was also lost with a thinner atmosphere, not being able to hold on to it. And so Mars, if it was a little bigger, even in that spot it is further away, might have been a better place for life. But without that core doing exactly what the Earth is doing, it lost the ability to hold on to its livability, really.
Yeah, and just to add, there's this really interesting sci-fi movie called The Core that is definitely sci-fi, but the plot of the movie is that if the core stops moving, then our magnetic field gets messed up. So who knows?
All right, well, I think we have time for one more question at this point. And since we were just talking about salt in the oceans, Sarah, maybe you know the answer to this question. Why does the Dead Sea have more salt than other oceans?
So I think there's a couple reasons. The main reason is that that area is extremely hot. So there is a lot of evaporation. So there is more water being evaporated out than there is water going in. And I think I'd have to look it up again, and feel free anyone to correct me, that the Dead Sea is actually getting smaller and more salty because they're taking out a lot of water for farming and agriculture. So a lot of our water is being depleted because of the space and water that we need for farming and for keeping livestock like animals, especially cows. So anytime that we take water out of an area like that, then we're leaving behind the salt. And that is true with evaporation. Usually salt is not going to evaporate up like the water does.
All right. Thank you, everybody, for asking your questions. Thank you to our educators for answering those questions. If you guys would like to say one final goodbye.
Bye, everybody.
Bye.
And thank you, everybody, for bearing with us as we had some technical difficulties during the show. We're so happy that you were able to join us today. If you would like to hear about more of our live offerings in the future, we've got a whole lot of them. You can check it out at mos.org/mosathome. And if you enjoyed today's presentation and would like to contribute to help us continuing MOS at home, feel free to visit engage.mos.org/welcome. Once again, that's engage.mos.org/welcome. Thank you again, everybody, for joining us today. And science never stops, so we hope to see you back again soon.